Hello and welcome to Sunday's edition of Cracking the Cryptic, and a puzzle that has been recommended by just about everybody, it seems, who's had a go at it. You can see it's a 4x4. It's called Sharing is Caring, and it's by none other than the Pedaling Pianist, who actually made another 4x4 that was deceptively difficult. This one has mad rules, so we've got to put the digits 0 to 9 once each into every row, column and 2x2 box. Now there are a lot more digits than cells available therefore, and we seem to be able to manage this therefore by putting up to 4 digits in one cell. It's completely bonkers, but as I say, we have had so many recommendations to do this. Apparently it is brilliant, and we've also had a few requests, even though I think this puzzle has, it's either 3 or 4 stars for difficulty on Logic Masters Germany, but it's causing some people no end of trouble, so I suspect it is not as straightforward. Well, not straightforward, but 4x4 you always think, oh, I must be able to do them. You can sort of bifurcate to them if you really need to, but we'll have a look at this in a moment or two's time. I've got some things to tell you about first. We'll start off by mentioning that there is a little bit of Cracking the Cryptic on the latest video on the maths channel Numberphile. A great privilege for us to be featured on Numberphile, so I will try and remember to put a link on the screen in case you want to check out the fact that not only is it really true that Cracking the Cryptic is on Numberphile, but you actually get to see my sideways profile, which you'll never see from this angle. Apparently it shocked some people. I don't know why. Anyway, other things to tell you about. Well, already about 1,000 of our patrons have watched the video that we released on Patreon only last night, which is a 2.5 hour solve, where I take on a puzzle called COASTER NURIKABE, which I think I can show you here, by the Cogito. It is a baffling and brilliant puzzle, and incredibly difficult and incredibly hard to even imagine how it exists, but I was actually really pleased and a tiny bit proud to see that the Cogito had themselves commented on the puzzle, or on my solve of the puzzle, to say that it wasn't such a bad effort. So that's really good. And if you are a patron, as I say, that video is over there right now, along with, of course, all the fun of the fair, which is our competition for this month's prizes. Now, other things I can tell you about. Loads of people have been tweeting to us to tell us that your books, Cracking the Cryptic's Greatest Hits Volume 2, has arrived. That is fantastic. So if that does give you a warm glow when it arrives through your letterbox, do drop us a tweet and tell us. And then I've got some birthdays to do. 3 birthdays to do today. We'll start off with Ali. Ali, it's your birthday today, and I know this because your boyfriend Mike wrote to us. And Ali, I think you're the one who watches and Mike goes to sleep to our dulcet tones or something. So Ali, I hope you have an absolutely brilliant birthday today, with loads of chocolate cake, of course. Now, the next 2 birthdays are a day late, but I hope not $1 short. Julia, over there in Nova Scotia. You turned 20 yesterday. Many congratulations. I know you were planning on having cake. I'm not sure what variety, but I hope it was chocolate cake with an enormous amount of icing, of course. And then Levi, you turned 18 yesterday. And you've been watching for about 1.5 years. Well, thank you for watching, and I hope that you were able to have a suitably epic celebration at reaching the grand young age of 18. And that's the birthdays done. Let's have a look at Sharing is Caring, and I will formally read you the rules of the Pedaling Pianist's latest monstrosity. What we've got to do is place the digits 0 to 9 once each into every row, column and 2x2 box. I mean, that feels so wrong even saying that. Cells may contain up to 4 digits simultaneously, and cells in the same row, column, box may not contain the same number of digits. Oh, I see. Okay. So that means in row 1, there is one cell that has 4 digits, one cell that has 3 digits, one cell that has 2 digits, and one cell that has 1 digit. And the same will be true for columns and boxes as well. Okay, that's a little bit strange. a cell's value is the sum of the digits it contains. And then values separated by a white dot are consecutive. So if this square was a 6, let's put 6 in there. If this square was a 6, although that's it's very unlikely to be a big 6, isn't it? It could be 6. It could be this. Now I think about it, it could be that adding up to 6. Oh, this is frightening. Okay, but if this was 6, this would have to have a value of 5 or 7, but that could be made up of lots of different numbers. And then values separated by a black dot are in a 1:2 ratio, so we've got loads of those sprinkled about. So that means that basically one of these cells has a value that is double the other. And values separated by an x sum to 10. So those two sum to 10 and these two sum to 10, but these can have any numbers of digits in them. Well, any number up to 4. Do have a go. The way to play this 2x2 puzzle is to click the link under the video as usual. But now I get to play. Let's get cracking. And I think we can start this straight away actually by thinking about this column, because surely we can do mathematics using a secret that I normally only share with my very favourite people, but of course if you're still watching this video 6 minutes in, you're definitely one of them. And the secret is preserved today by the fact that even though we're using 10 different digits, one of the digits is 0. So the secret still applies, the basic Sudoku secret, which is so silly doing this in a 4x4. But the secret is that any row, any column, and any box of a normal Sudoku adds up because of the rules of Sudoku to 45, because that is what you get if you add 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0 together. Now that still is true in this puzzle because we do have to put all of the digits into every row, column and box. Now, if we think about the structure of black dot sequences, let's say that this cell was an x, then this cell 2x, this cell 4x, this cell 8x, because we have to keep the doubling relationship going. And that means that this column adds up to 15x. Now if this column adds up to 15x, but we also know it adds up to 45, then x is 3. So this column goes 3. Well, the thing is, it might go backwards, it might go upwards 3, but it goes effectively, its sequence is 3, 6, 12, 24. So one of either this square or this square is a 24, and either this square or this square is a 12, which obviously we're going to have to do with a multiplicity of numbers. And this square is not a 12, and I can see that fairly clearly actually, because if this square's value was 12, then by white dot language this square's value would either be 11 or 13. And although this puzzle is quite ludicrous, it doesn't have negative numbers. So if this was 11, we can't put -1 here to make the domino add up to 10, and if it was 13, we can't put -3 there. So actually we know the structure of column 1 straight away. It is, we need this to be low, so it's got to be, okay. Well, what I was going to say, I was going to start putting digits in here, but that's not going to work, is it? Because we've got to find, maybe we deal with values to start with. So the values of these digits, 3, 6, then this is 12, which I don't have a good way of writing in, but we can probably do it using my normal patented method of trying to put double-digit numbers into cells. I could do it like that, and then this is 24, which is going to be, actually 24 we'll get away with because they are, actually 12 I can do as well. Hang on. Yeah, sorry, it is easy to do. 3, 6, 12, 24. And now, whoa, this is hugely powerful. This is hugely, so this box overall, don't forget, it adds up to the secret, which is 45. But these two squares add up to 36 already. So these two squares add up to 9, and they contain consecutive well, consecutive values. So this is some sort of 4-5 arrangement in one order or the other. But maybe it's here that's easier to start with, because this square's value is 5 or 7. Because it's got to be sequential with 6. And what did I say this one was? Hang on. That's a black dot, isn't it? That's not good. That's troubling. That's going to be... Hang on, what's going on here? I can't make that work. What have I've done something wrong. What? Sorry, something wrong. What was that? This is definitely 36. These definitely add up to 9, but the values add up to 9. The values are consecutive, so they must be a 4-5 pair in some order. So this cell here, I think, has a value of 4 or 5, but it's on a black dot with a cell that has a value of 5 or 7, and it should be in a ratio of 1 to 2. I don't think that 4 or 5 is in a 1 to 2 relationship with 5 or 7. Hang on, did I get the maths of this column wrong? X, 2x, 4x, 8x, that is 15x, that is x equals 3. So, and then that can't be a double, well, it could be a double digit number if it was a 10, but it doesn't have the luxury of being a 10. Because if it was 10, this could be 9, and then that would make that possible to fill. Although, no, I was about to say that wouldn't work for the black dot, but it would. If you can't put 4.5 in here, but you could put 18. I'm so sorry. I've done something wrong, and I haven't got a Scooby-Doo what it is. There is no way this can be 12. There is no way. I hate this. I hate moments like this because I feel like my brain's broken. I feel like I feel like numbers don't work, and this is completely. I don't understand. I don't understand. I must have misread the rules, I think. Place the digits 0 to 9 once each. Cells may contain up to... I haven't even thought about how many digits are in cells yet. A cell's value is the sum of the digits it contains. So, I must have done something wrong in this column. But if that's x... Oh, I didn't think of that. I didn't think of that, he said. What's Captain Beaky? That's Captain Beaky. Said reckless. Said somebody. Said timid toad, I've got a wheeze. No, said, oh, no, so timid toad, I've got a wheeze, we'll fly above the trees and drop a boulder on his head. Said, artful owl, I like your plan, how will you get it off the ground? Oh, I hadn't thought of that, he said. Oh, I don't know, I can't quite remember it. That's really annoying. That's another annoying thing. I hadn't thought of that. I was just thinking, I have been assuming that this goes x, 2x, 4x, 8x. But it doesn't have to do that, does it? So if this is x, well, if that's x and that's 2x, we don't have to necessarily go to 4x. We could go x, 2x, x, 2x. No, that also, well, it's a better thought. It's definitely a better thought, but it doesn't work. Because x plus 2x plus x plus 2x is 6x, and 6 does not divide exactly into 45. So you could never make the x work. Right, so what we've got to do is go x, 2x, 4x, 2x again, which is 9x. Okay, it's 9x, and 9x does divide into 45 to give x equals 5. Right. Oh, this is far cleverer than I gave it credit for. I mean, I shouldn't be that surprised. It's the pedaling pianist after all, but this is... Yeah, I've spent 15 minutes being a bit of a doofus here, I think. Right, so the only thing that's worrying me now is if it was quite simple this when I was assuming it went x, 2x, 4x, 12, sorry, 8x. But if I'm just going x, if I need to have x, 2x, 4x and 2x, do I necessarily... No, I don't. Oh, this is awful. This is awful, because this introduces lots of other possibilities. Because you could go, I think, 2x, x, 2x, 4x. Okay, so what we're actually doing here, this is brilliant. This is absolutely brilliant. So what we've actually got is... Right. What we've actually got is, because now we know x is 5, 2x is 10, and 4x is 20. Now in this column now, so we could have, let's try and do this, we could have 5, yeah, okay, that's going to work. Where's it going to put the 0? Not in the right place. Let's put the 1 there and then put 0 here. So we could have 5, 10, that's 2x, 20 we then need, which I'm going to have to do it this way again, 20, and then back to 10 again. Let's keep, this is troubling, but something like that. So we could have this, and that looks quite good actually, because that would allow this to be 9. That to be, oh no, that doesn't work. Okay, I'm not going to focus too much on this, but I think that might not work. Where the 2x's are there, but you could also, well, you could invert this very straightforwardly. So you could have the 10 here. You could go 10. Actually, that's trivially disprovable. You could have, but you could have 10, 20, 10, 5, couldn't you? Just by inverting this sequence. But here's the thing: you could also have. You could have a 10 on the boundary, like this 10, and then go 5, 10, 20. So the 20 wouldn't be in one of the two internal points, it would be on one of the edge points. So the only thing we do know for sure is that the two x's, which are valued at 10, are separated by one cell. So that there's either 10s in both of these squares or in both of these squares. But then the 5 and the 20 that sit between them can go in either order. So there's a lot of possibilities here. I think I might stick with this one though, because I think that it might be possible to remove the possibility of 20 being an internal number. Let me show you why. If we invert this, so it goes 5, 10, 20, 10, this would be a 20. this would be a 19 or a 21, and clearly this x breaks. So it's not an inversion of this logic. If it's 5, 10 though, this can't be 11 because that can't be -1. And if this is 9, the value of this is either 4.5, well that's not possible, or 18. Now if it's 18, surely I've got too many values in this box, which should add up to 45 and already adds up to 48, and that can't be -3. So I think we're in a world where these are wrong. So what we've got to do is not invert. We're going to have a 5 in the middle of the grid, but it could be here. It probably is here actually. But let's have a think about that in a moment. And this is going to be a 20, but again this could be the other way up. So we're either going 10, 5, 10, 20, or we're going 10, 5, 10, 20. Now, well, I can trivially disprove this version. So I think I've got one version left that works. The way I'm going to disprove this version is by parity, because the values along a white dot are going to be odd, aren't they? One of these values is odd and the other is consecutive with that, so it will be even. So collectively the values of this dot are odd. Well, the value of 5 and 10, those two are odd as well. That's 15. But that means that we're adding an odd number to an odd number to get an even number, and we know that box adds to 45, which is odd. So that's wrong. So this is not right. So in fact, I think what we've got to do is, it's all, yeah, so we've got to completely invert this. So we're going to go 20, 10, 5, 10, I think. And this better work, or I'm out of ideas. So I think we go 20, oh sorry, I'm trying to do this, it's difficult to do this, 20, then that must be 10, which is going to be like this is going to be 5, and this is going to be 10, and that does give us 45. Now this needs to find a way to work. I mean, it looks better, doesn't it? Because this square has a value of 4 or 6. That's quite funny. So this square has a value of 4 or 6 across the x, and this square, hang on, right, we've got 30's worth of values on this dot, so these have to have 15's worth of values to make 45 for the box. They have to be consecutive, so this is an 8, 7, and that's better. That is better, because if this has a value of 8 or 7, but it's on a black dot with a 4 or a 6, we can make it work now if we make that 8. So that's 8 value, that's 4 value, that's 6 value, that is 30 value. This is brilliant. It's absolutely brilliant, because look, the row must be 45, and that's 15, and 30. I can only see one way of making that work with 4 digits, up to 4 digits in a cell. So we're going to come back to that in a moment, but let's just carry on working here. This is a 7 to make the mathematics of this box work. What's the mathematics of this box? We've got 19. That's a 26, which is, oh no, hang on, I can do that. I can do that like that. That's 26. This is 36 already, so these add up to 9, but we don't seem to know anything about, it doesn't give us a dot or anything there, does it? So that's less clear what's going on there. Okay, and let's, we can carry on, look. This has a value of 5. And the way to see that is to look at this column where we've got 10 plus 30, we need 45 overall. So that's a 5 and that's a 4 then, by the mathematics of getting to 45 in the row. This is a funny domino, because we don't know anything about it apart from it. Well, no, that's not true. We can deduce something about it. We know that the 2 values here sum to 35, so they're quite ginormous. 10, obviously 45 minus 10 for the x domino. Right, so now somehow we have to populate these cells with the right numbers of digits. Which feels, does that feel like it will be easy or not? I think, well, we obviously start here. So this is going to be, the challenge here is going to be to work out how to notate this. Because I want, well, I need to put, I know this has got 6, 7, 8 and 9 in it. That is a real cell. That is a real fill for the cell. As in, that would be in the final answer that I submitted in an exam situation for this cell. That cell is correct. And, okay, so we know that one of these has to be a 3 cell, because this, in this row there's only one 4 cell thingy, and it's that one. So one of these low numbers has to be 3 cells. Oh, but we've got 0, haven't we? We've got 0 as a possibility, so we can actually, that's quite easy. Even the 4 you could make work with 0, 1, 3. Okay. Oh, no. Well, which one of these? Yes, in every row, column or box, there must be a cell that has only one number in it. Well, look at this column. We've got a 10. I can't put one number there. I can't put one number there. I can't put one number in a 20. So that's one number, which is a 5. So again, in my final answer, I'm submitting that cell. Now, do we colour that purple to say that it's it's correct and complete, or do we colour it hang on. Yeah, okay, what we might do is not colour it purple. I might colour that something different. I'll make it orange for a moment, because what I'm thinking is this is weird, but I think what we need to do here is to somehow play Sudoku with the number of digits in cells. So what do I mean by that? Well, this is the only cell now in box 1 that has only one digit in it. So one of those squares must be a 1-digit number. Now, does that have to be the 5? So I know by Sudoku 5 is in one of these 2 squares. So if that was a solitary 5, then these 2 squares by Sudoku would have exactly the same composition. So if this was 0, 1, 3, that would have to be 0, 1, 3. But is it possible that's a solitary 4? If that's a solitary 4, that couldn't be a solitary 5. Oh, I see, that could be 5, 0. Oh, good grief. Right. So I don't, even though I want to, and I suspect it's true, I'm not sure logically you can justify just writing 5 in here as a big number. I think there is still the remote possibility that that is a solitary 4. Yeah, and then the 0 would switch places. So if that's a solitary 4 and that's a 0, 5, then 0 in row 2 has to be in this square, which would be a 2-cell 0, 4. And we'd have 0, 4, 5 here as in totality, and 0, 4, 5 up there in totality. Now, okay, well, can we play the same game then with purple? So one of these, surely this one, has to be a 4-cell purple digit. Now if that was oh no, I was about to say if that was 4 cells, it would have to be 1, 2, 3, 4, but 0 is a possibility again. I mean, that has to be a lot of digits. Yeah, but you could make 8. You could even make 7 with 4 digits in this puzzle. This is tricky, actually. This is tricky. Okay, here is a point, I think. Surely I need a 9 in this one. Oh, hang on, no, it's too big. This is the 4. It's too big. That's what I hadn't appreciated. If this was 987, that's 24, isn't it? I'm confusing myself here. So this must be 4 cells. And it's got a 9 in it, is what I'm now going to claim. Because if it didn't have a 9 in it, it could only be 876, and then it couldn't have the 5 it would need to get to 26. It would be 8764, and I think that's one short. It's 25. So there is a 9 in this cell. It is a 4-cell sequence. Ah, okay, but it hasn't got 8 or 7 in it. This is fascinating, actually, because again, by Sudoku, the single-digit total in column 2 is not up here. So it's 8 or 7. One of these is a real number, a real boy. So that means, imagine this was an 8, a big 8. Then you couldn't put 8 in the 26. And if this is a big 7, you can't put 7 in here. Now, so does that mean this needs to have 6 in it then? So let's say it had 9 and 8 in it, 17, and it didn't have 6. If it didn't have 6, the next two biggest numbers would not be big enough, I don't think. 17 plus 4 plus 3 is not 26, is it? So this does have 6 in it. So it's got one of 7 or 8 in it as well. Now, okay, so if this has 8 in it, then it's got 23 and it needs another 3. If it's got 7 in it, it needs another 4. So it's either 9647 or 9638. Oh, that's interesting then. So, and whatever its low digit is, which we've now worked out is going to be a 3 or a 4, where does that 3 or 4 go in this row? Because these two digits are real now, so that digit's going to transpose here. So this 6 value has a 3 or a 4 in it. Yeah, but that's not... that's really not actually that helpful, I don't think. Because it could have 3 in it. I mean, ordinarily we'd look at that and go, no, but it could have 3, because it could have 1 and 2 as well. So it could be 3, 1, 2. 3, 1, 2. And then that would be 4. And somehow you'd allocate the 0 to one of these numbers, depending on which one you... Well, actually, if that was 3, 1, 2, the 0 would go here, because this couldn't be another 4-digiter, because we've got the 4-digiter already. Okay. So this one is either a 2-digiter. If it's a 2-digiter, hang on, then it depends what we've put in here. If this was 6938, that couldn't be a 2-digiter, I don't think, because it couldn't be 19, it couldn't be 28, it couldn't be 37, and it couldn't be 46. But this is that's predicated, so that would be a 3-digiter, and that would be a 2-digiter adding up to 4. But that could still be 40. Oh, the 0 being a possibility is so horrible. So if this is a so that would be a 3-digiter. I can't even think what it's going to have in it then. It's going to have something like 712 or something, I think. Yeah, 712 is a 3-digiter. Oh, but hang on. Alright, the 5 that is in row 2 at the moment can't go in the 4 square in row 1. So that there is a 5, there's a 5 in the 5 cell, but we don't know whether it's on its own, because it could have a 0 in it. Oh, this is ridiculous. Oh, yeah, okay. So this domino, adding up to 10, contains all of the... It contains 1s, 2s, 3s and 4s in some disposition, but it could also have 0 in it. Oh dear, this is tricky as, isn't it? This is very difficult. So these add up to 10, but there might be another digit in there. If there was another digit, it would be a 2 and a 3 split, and then that would be a 1 seller. But if this is only 4 digits, it's a 3 and a 1, and that's a 2-digiter. When I say a 3 and a 1, I mean it's a 3-digiter and a 1-digiter. Either. Oh. Okay, so maybe we've got to think about... Maybe we've got to think about maths again then. That looks like it's got to be quite a big digit. The problem is that that cell could be big. Well, not big, but it could be. It could be a 3-digiter. It can't be a 4-digiter, so it can't have a value of 10. But it could have a value of, say, 2, 3, 4, and have a value of 9. So the maximum value of that is 9. 17, 27. The minimum value of this square is 18. The minimum value of this is 18. Now, what does that mean? 18, 28, this would be 17 in that situation. So this is 17 or lower. Oh, but one of these is the 4-digiter, because the 4-digiter isn't in those two squares in column 3. And what's going on in this row? Well, it depends again, doesn't it? It depends what this cell is, which is up to 9. So if that's 9, we've got 27, 36. Then this square, 36, this square would have a value of 9. Which is probably interesting somehow, some way. Oh dear, okay. What do we do then? How do we do this? Do we do frivolous things like say that cell is some number of digits, which is 2 or 3, and therefore by Sudoku there is a green up there. So this is a combination of the green number of digits and the orange number of digits. So we could make this, I don't know, I make this yellow. So that must be yellow. So these two have the same number of digits. Yeah, so yellow goes down there. I don't know if this is in any way helpful. This is a purple-green pair. One of which is, so one of these is a 4-seller, one of these is a green seller, whatever green happens to be. But the problem is, even though green has a very low value, green could be anything. Well, not anything, it could be 2 or 3 cells. Okay, so this is a single digit 7 or 8. Gosh, this is difficult actually. This is actually very difficult. I don't see. One of these is yellow. What's yellow when it's at home? Yellow is yellow's a 2 or a 3. But we don't know, because we don't know what this is. That could be a 1-seller, in which case there's a 1-seller here. Or it's green, in which case this is green. This is a 1-seller, and there's a 1-seller down here. Yeah, oh, no, hang on. If there's a 1-seller down here, it's got to be there, doesn't it? Because that, I think I said that added up to 18 at least. Was that wrong? How do we minimize this? We maximize this. So that's 9, 17, 20. Yeah, that's at least 18. So if there is, yeah, so if that's, let's just have a think about this. So what I'm saying is, if that is the single digiter, then that is a single digiter. And that would mean, what would that mean? 27, 36, this would be a 9. That, oh, I can't, does that work or not? Where does, no. Oh, wow, okay, well I've managed to disprove this. This doesn't work. This is not straightforward, but it doesn't work. Okay, here is my thinking. So what I was saying was, if I'm just trying to place the single digiters around the grid, and because I know this cell here can't be a single digiter, if this is a single digiter in box 2, this is a single digiter. But the interesting thing about this square is there's only one way it can be a single digiter because of what's in its row already. And the only way we can keep this down to being a single digit number is by maximizing this, by making it add up to 9. So it would have to be a 3-digit 2, 3, 4 triple. Because if it's any lower than that, this has to be a double-digit number. But if it was a 3-digit 2, 3, 4, and this is 7 and this is 20, then we've got 36 here, so this can be 9. But now we've got a problem, because we have to put 5 in this row. Now where are we going to put 5? Well, we can't put it here, and it doesn't go there, so it's got to go in here in some capacity, with some digits that add up to 7. Well, the only digits that we could put in here to make 7, if one of the digits is a 5, we're going to need to put a 2 in. But we can't put a 2 in because there's a 2 in this square in the 2, 3, 4 triple. So it doesn't work. It doesn't work. So what that proves is that this is not a single digiter, which means that is a single digiter. So that is giving us a digit. That is a real 4. That is not a real 4. A real 5, I should say. Right, so the only way this could work... Oh, this is big, because now we know the nature of green. When I say we know the nature of green, we know how many digits are in green. Because we know there's a 5 in this cell by Sudoku. So it can't be accompanied, but with anything else other than 0. So this is a 5 and a 0, like that, which means this is a 0, 4, because the 0 needs to go somewhere in this box. So green is a 2-digit number. So yellow is a 3-digit number. And in fact, we can see in this row, we can just put in here the digits that we've not used. We know that they must add up to 6, and indeed 1, 2, and 3 do add up to 6. So these are orange and yellow. This is a 3-digit number adding up to 10. Okay, we can probably do that somehow. Do we know what that one is now? I don't know. I don't know. This one. We advanced the cause here. I think we must have done. Just have to think about it for a second or two. This is green, purple, and this is 3 digits that add up to 10. Not including a 0. Oh, I see. That does it. Oh, this is so. I mean, sometimes you just realise when you're solving these puzzles. Actually, it's quite often that you're in the presence of genius, because this is genius. It's filthy. It's absolutely filthy that this can solve. It's so stupid. But look, we know that this has got 3 digits in it now, not including a 0. So the minimum we could put in here would be a 1 and a 2 and something else. Well, we can't put 8 in there, can we? Because 1 plus 2 plus 8 is not 10. So it must be the 7 that's going in here. No, I actually want to put digits in. I want to put a 7 with a 1, 2 pair. And that will allow this square to be 6, 9, 8 and 3, I think, in order to get to the right total. So that's 6, 9, 8, 3. This is 1, 2, 7. So the 7... so the 7 is the digit... did we actually... I want to say the 7. We know one of these is a single digit, and I want it to be the 7 now. Yeah, it can't be the 8, can it? Because there's already an 8 in the column. So the 7 is a single digit total, which is orange. So this is a yellow digit. So this is a yellow way of making 8, which is a 3-digit way of making 8. Oh, and it's just going to be the digits in the column we've not used, which is 1, 2, and 5. Okay. So that square is now not 1, 2. Oh, in fact, this is a single digiter, isn't it? By Sudoku on the orange digits. So this is a single digiter. This is a 3-digiter. And there's definitely a 1 and a 2 in this, and then either 3 or 4, depending on what this is. Now, how do we work this out then? It would be very good if this was totally obvious. I'm sure it is somehow. I've just got to figure out how. So the 0 has to go in there, doesn't it? The 0 has to go in the 20. And I think the 9 has to go in the 20 as well. Because if the 9 goes in the 10... Oh, hang on. The 10 could be... No. Okay, so the question now that we ask is it possible for the 10 to be the 4-digit total? And because 1 and 2 have gone, I don't think it is, because we could put 0 in here, but then 3 more digits, which would be at least 3, 4, 6. That adds up to more than 10. So the 20 is the 4-digit total. The 10 is the 2-digit total, which means this is a 2-digit total and this is a 4-digit total. And now, oh, I see, that's beautiful. Right, 1, 2 and 7. If this is a 2-digit version of making 10 that doesn't involve a 1, 2 or a 7, It can't be 1928 or 37, so that's 46, I think. Which means this is 3. This is so brilliant. It's brilliant. Now that is a 124 triple in the corner. This is something which is whatever's left over by a process of elimination. So it should be digits that add up to, it's 389, which do add up to 20 along with the 0. And now it should just be Sudoku. This square is 0, 7, 8, 9, which is lovely. So that's a maximum digit. And this square is a 5 and a 6. And look, it works. In this column, we've obeyed the rules of Sudoku. I've got no idea. Is it going to know? The puzzle is not yet finished, but the digits you've entered are correct. Oh, okay. Oh, maybe if I put a 7 in there, maybe it'll like it more. It does like it more. Solve counter 3 in 3 days. That is fantastic, isn't it? That is absolutely fantastic. I'm sort of lost in admiration for that. It's also surprisingly difficult. Oh yes, and that's dragged me back to the start of the puzzle where I'm sure I was getting shouted at a lot. I'm very sorry. I saw this and I thought, oh, I can do the maths. And I could see the algebra. And the algebra seemed to work. And yet it didn't at all. It didn't at all, did it? But it was beautiful. It's beautiful that this collection of dots and this X with the white dot here and this black dot here leads to only one of however many iterations there were of the ways that where did we end up? X2, X4, X2X. Only one of those ways worked. And then from there that you could actually disambiguate this. It's magical. That is magic. It's taken me a long time, but I loved it. Sharing is caring indeed. The Pedaling Pianist, thank you again for, showcasing your genius before us all. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind, especially after that introduction. And we'll be back later with another edition of Cracking the Cryptic.